Alright, we're going to try factoring a difference of squares. So we remember that whenever you see only two terms in the expression, that's already going to be a hint for you to check that maybe that's going to be the factoring strategy you need, the difference of squares. So just off to the side, as a reminder, we have seen the difference of squares pattern before. A squared minus b squared would be equal to the sum of two terms multiplied by the difference of those same two terms. So that's just the general case to remind ourselves what we actually have to do here. And then we would say, all right, we want to basically know if this is following the pattern of a squared minus b squared, what would be the value of a and what would be the value of b. Because then it'll allow us to rewrite it in the factored form as the binomial times the binomial. So the way that you can actually figure this out is simply by taking the square root of each of the terms in the original expression. So the square root of x squared is going to become x. And then the square root of 100 is going to be 10. So this is something that you could have also checked on your calculator for if you ever needed to, but if you remember all the perfect square numbers, it makes it go a lot faster. So now we know this is basically our a term, the x, and there's our b term. So what this is going to mean, since a squared minus b squared equals a plus b times a subtract b, x squared minus 100 in the factored form will be x, that was our a term, plus 10 multiplied by x minus 10. And then that would be our completed answer there. So let's try another one where we're going to factor another difference of squares, but in this case it's going to be not a coefficient of 1 in front of the x. So in this one we're going to factor 4x squared minus 49. And once again, just as a reminder, I always like to write the general case for the difference of squares, which is going to be a plus b times a minus b. So we have the two terms here. So this is basically going to be our a squared, and this is going to be our b squared. So when we want to know the actual value for a and b, I didn't show this in the last example, but I'll just review this. So the square root of whatever this term is will give you a, and then the square root of whatever that term is will give you b. So first, we want to know the square root of 4x squared, which is kind of like saying we want the square root of the coefficient multiplied by the square root of the variable term. So just like when we were doing common factors, you still have to look at two parts separately. You have to look at the number part and the variable part. So the square root of 4, we know that that's 2, and then the square root of x squared, we know that's x. So that means the a term is going to be 2x. And then just off to the side, a way that we can actually prove that we've done that correctly, like if you want to know why is the square root of x squared equal to x, we can just try multiplying those two things together again. So 2x times 2x, multiply the numbers and multiply the variables. That's like saying 2 times x times x, 4x squared. So we did do it correctly. You don't have to do any of that stuff in the purple. That's just to double check. So 2x is our a term, and then for the b term it was the square root of 49, which is equal to 7. So this would be the b term. So therefore, when we're factoring 4x squared minus 49, and we want to make it fit that general term, that general pattern, the factored version is going to be 2x plus 7, because it's like a plus b, multiplied by 2x minus 7, because that's the a minus b. So that would be our final answer there. Alright, we're going to try one final simple difference of squares, as in does not require any other steps or common factor or anything, just pulling out the a terms and the b terms. So as a reminder, our general case for the difference of squares is when you have a squared subtract b squared, which is the form that this expression is in that we're going to factor. You can factor it into a plus b times a minus b. And we know that a is going to equal the square root of this term, because this is a squared. And then b is going to equal the square root of b squared, which is that term, the 16. So let's find the square root of x to the power of 6. And then for this part, I am going to show you the actual exponent rule for why this would work. So whenever you have a square root is the same as raising something to the exponent of 1/2. So this term is actually equivalent to writing x to the power of 6 to the power of 1/2. And then from here it becomes an exponent rule that we've seen before, where if you're doing a power to a power, you just multiply the exponents together. So x to the power of 6 and then 6 times 1/2 is going to give you x to the power of 3. So that's our first term. This is going to be the value of a. And then if we just want to check our work, because a lot of factoring is self-checking, if we just say x to the power of 3 times x to the power of 3, well, then it's going to be x to the power of 3 plus 3, which is x to the power of 6. We did it right. You don't have to do any of the work in there. That was just to prove that we had done that step correctly. So after we have this, now we need our b term, which is the number. So the b term is going to be equal to the square root of 16, which in this case is 4. So that's just something like time on your math facts is never wasted. We just know the square root of 16 is 4. 4 to the power of 2 is 16. So that's going to be our b term. So now once we have that, now we can actually factor. If we have x to the power of 6 minus 16 and we're factoring that, it's going to fit this general pattern, a plus b times a minus b. So it will be, that was our a, x cubed plus 4. And then the a term again, x cubed minus 4. And then that would be our completed example and the completed answer. Oftentimes for difference of squares, you won't necessarily have to do all of the work to get the final answer. And then in a lot of cases, if you can complete the question just by making it fit this general case, but this is proving how we got to those numbers. Over time, you'll get quicker at just picking out what the perfect square numbers are and then factoring it really quickly.